Dr. Sabbir Vasa is a currently associate with RV University Bangalore as an associate professor. He completed his PhD degree at the IIIT Sri City, Chittoor in 2020. After PhD, he has worked as a technical lead for the Path Partner Technologies Private Limited, Bangalore. After this, was associated with Latex in as a senior machine learning scientist. During this period, he worked on neural network compression, domain adaptation, multitask learning, and active learning methods for solving computer vision problems. He possesses a high level of proficiency in project development and research, specializing in the domains of computer vision and machine learning. He is an active reviewer of several reputed journals such as IEEE Transaction on NN LS, neural network, neurocomputing, pattern recognition, WACB, and many more. His research interests include neural network compression, active learning, domain adaptation, multitask learning. So, welcome, Dr. Sabir. Now the session is over to you.
Yeah. Thank you, Professor. Thanks for the invitation. I think we are delayed by 6 minutes already. Without further delay, let me get started. Could you please confirm, is my screen visible?
Yes, yes.
And my audio is clear, right?
Yes, yes.
Okay. Yeah. Thank you. Yeah. Good morning, everyone. Today, I would like to talk on two topics which are very hot in the research. One is few shot learning, and the other domain is active learning. So throughout this talk, I would like to give, I will not get into in detail about these topics, but I'll try to give some intuitive understanding of why they are essential when we are working with some hard problems in research. And also wherever is needed, I'll give some industry related examples for you. This is the outline of my presentation today. First, let me just motivate where we are. As part of this talk, we are going to talk about how to manage to get better and better deep learning models with limited data, limited supervised data. So that is where this talks focus on. Now, let me just set the motivation behind these two topics. Yeah, first, as we know that these deep learning models are data hungry models. So we know that as we have more and more supervised data, then we can train our models using that supervised data. Then we are expected to get better results. But on the other hand, we should also make sure that from task to task, as the difficulty level increases, we are also need to concerned about the cost incurred with annotation. For example, if we take just object recognition, where the annotation cost per sample will be lesser compared to annotating for object detection task. Similarly, object detection task annotation will be lesser compared with semantic segmentation task and so on. Now, so here I would like to talk on what are the different methods that people have been trying to reduce this annotation cost. Yeah, one thing is, so let's assume we have completely unlabeled data, but I'm not interested in labeling that images from the beginning, but can I do something called semi-automated labeling? So this is where instead of labeling data from scratch, what we could do is we could use some models that using which we can get the detections. So instead of annotating this bounding box for every people or for every object, what we can do is we can feed this image to a model. Model will give these predictions. These predictions we can use as pre-labels, but with the human review, we are going to review and label whatever are the objects that are missing. For example, in this case, model is unable to predict this person, this object. So with human review, we are going to achieve that. So that is, even this semi-automated labeling, we need human intervention so that a human can verify whether these predictions are valid or not, and also if there are any missing predictions, if there are any predictions missed by the model, that the human has to label manually. Now, this is one way of handling to reduce the annotation card. And the other direction where people started thinking is, could we manage to train the models with limited number of images, or in general limited number of samples? So that's where there are different research domains, something like semi-supervised learning, few shot learning, zero shot learning, unsupervised learning, and active learning. So where so they are going to make use of these different methods in order to make the models to train with a limited amount of data. So as part of this talk, let us try to constrain our focus on few shot learning and active learning. Before we get into few shot learning, just let me talk about how it is different from supervised learning. As we all know that when we are going to train a deep neural network for supervised learning tasks, something like object recognition or object detection, we are going to have a large training set using which we are going to train this model, which we call it as a pre-trained model. Now, so once we have a trained model, then so we are going to have an unseen image. So this unseen image, we are going to give it to the model, and we are going to see what the model is going to predict. And one fortunate thing here is this unseen image. This is actually from the same class. So the class that it has seen, that the model has seen during the training. The sample may not be exact. The sample may not be present in the training set, but this sample is from the one of the category of the training set. Now coming to few shot learning, whereas in few shot learning, our objective is to get the model prediction for a sample where this sample is not present in the training set. Even the sample category is not present in the training set. For example, if we take here, we have 5 categories. Of these 5 categories, so this query sample category is not present. Basically, this is actually rabbit. This category is not present in the training set. Uh, Here, this is the setting that we are going to talk about in the next few slides. So before getting into the working of few shot learning and what is the intuitive understanding and what is the idea behind few shot learning, let me just introduce some terminology here. We have something called training set. As we know that training set is nothing but the large data set that we can use to train the deep learning model. Then we are going to have support set. So if you look at the previous slide where this query sample is completely from a new class. Now, so we need some additional information which is called support set. This support set is going to have a few samples for each category. For example, if you see here in this case, the support set has 6 categories: fox, squirrel, and so on. And each category is having one sample. Now, we need this additional information called support set. This support set, we are going to feed it to the model so that our model will have the knowledge of the support set. So then we are going to have something called query sample. This query sample will be used at the time of testing. This is to say we are going to feed this query sample to the model, and we are expecting model to say to which category it is belongs to from the support set. Is it belongs to fox category, or is it belongs to rabbit category, and so on. Here one more thing. This is in general, this few shot learning is considered as K-way N shot support set. Basically, it is going to use a support set that has N classes. Sorry, that has going to K classes, and each class is going to have N number of samples. Now, let me define here what do you mean by K-way N shot, where K represents the number of classes that the support set has, and whereas n shot represents the number of samples each class is having. For example, if you take this example, in this example there are 6 categories, and each category is having one sample, so it is 6-way one shot learning. Whereas if you take this example, in this case, support set has 4 categories: squirrel, rabbit, hamster, otter, and each category is having 2 samples. So it is 4 class and 2 short learning. That is 4-way, 2 short learning. Yeah, with this terminology that we have learned about uh, few short learning, let me set the problem statement of few short learning. We are going to have a training set. Using this training set, we are going to train a model. This trained model can we make use for a problem where, so there is we are going to have a data set. That data set will have very limited samples, very few sample. It is not even like something like at least 100 samples per category. Let's assume we are going to have just maybe 3 samples per category. Now, how can we make use of this pre-trained model, which is learned using this big training set? Can we make use of this pre-trained model to make predictions on the samples belongs to the support set, but the support set has very few samples in each category. Now, you may think of this setting is similar to the tradition, the transfer learning, but it is slight different from transfer learning. So why? Because just let me differentiate how it is different from transfer learning. In case of transfer learning, we are going to have a pre-trained model, and that pre-trained model, whatever knowledge it is learned on the source task, that knowledge will transfer to the new task. Uh, so we say we are going to transfer the knowledge. We are going to fine tune the parameters involved in the output layer using the target data set. Whereas in that case, what will happen when we are going to fine tune in over the target data set, then the parameters involved in the output layer will be updated. Then it may do well on the target data set, but at the same time, it may not do better on the training data set. It means what? When you are going to update the model, basically you are trying to update the model with respect to the target data set. So with this, what will happen? The model may forget whatever it is learned with the training set. That is the base source data set. So this is what is called as catastrophic forgetting. Now, the objective of few shot learning is we have to come up with a model. That model is still it should do well for both training classes and as well as novel categories from the support set. For example, if training set is having 5 categories, for this 5 categories plus let's assume there are 3 categories in the support set. For all these 8 categories, we have to build a model that is going to do well. So it should not forget the knowledge about this any of the classes in the base data set or in the source data set. I hope the problem statement is clear. Just let me move on to the the major idea. Most of the papers they have published in the few shot learning area with this basic idea. The idea here is to learn a similarity function while training over this large scale training data set. Just let me explain how it can be done. First, we are going to learn a similarity function. For learning the similarity function, maybe I think we could use of pairwise similarity that people have tried with Siamese network. That could be one idea. And so the other idea could be the model can be trained with triplet class such that the samples belongs to the same class uh, in the feature space. The samples belongs to the same class should stay close to each other, but whereas the samples belongs to different class should stay far away from the samples belongs to other class. So with these two ideas, we could make the model to learn the similarity function. And during the prediction stage, what we could do is so we could feed each sample from the support set to the model so that we are going to get a vector. That vector, see basically if we feed this image to the model, we are going to get a vector. Similarly, for this image, we are going to get a vector. Now, at the time of prediction, you use query image. Similarly, for that query image, you get a vector. compare that vector. So now basically we'll be having two vectors. You'll be having a query vector, and you are going to have six vectors in this case, where each vector will be for one image in the support set. Now you have two vectors, just compare the similarity between those two vectors. Maybe the similarity function could be something like cosine similarity. You just see, so for example, let me illustrate this with this example. Let's consider this is the query image. If you feed this image to the model, it is going to give a vector. Similarly, if you feed this image, it is going to give a vector. If you compute the similarity between these two vectors, so you'll get maybe something like zero point 0.2 here. So the similarity between the query image and the image from Bulldog, you are going to get 0.1, 0.03, 0.05, zero point 0.7, and zero point 0.5, and so on. Now, what we are going to do is we are going to map this query image to the category for which we got the maximum similarity. So this is the basic idea, where there are many methods based on this idea. So instead of affecting the model performance and the training data set, we can make use of that pre-trained model to get the feature vector for every sample in the support set. That vector, we can compare the similarity between that vector and also with the query image vector. Now whichever image sorry for whichever support category we have the maximum similarity, we are going to map, the model is going to map that query image to that category. So in this case, it is going to map with a category called utter. And so when coming to the research in few shot learning domain, where so these are the two most popularly used image data set. One is OmniGlot data set. This is similar to MNIST data set. Yeah, please go through this website, so that this is much complex compared with MNIST data set, because it is going to have a very less number of samples per category compared with MNIST dataset. As we know that in MNIST dataset, we'll be having around uh, 5,000 samples per category, but whereas here there are around 200 categories, but per category we'll be having only 100 samples. There is one more dataset called Mini ImageNet dataset. This is actually a subset from the Mini ImageNet dataset. Yeah, please feel free to go to this link and download the data set. So these are the two mainly used data set to validate the few shot learning methods. Now let me just summarize when exactly we are going to use few shot learning. Few shot learning, as we understood that when we have a completely annotated data set, but of that there are some categories or some classes, they have very few images or very few samples. In that case, we are going to go for few shot learning. Here the few shot learning assumes a setup where we have a data set where that data set is completely annotated, but of those n number of classes, uh, a few classes will have limited training images. This is where the setting we go for few shot learning. Now let me raise another question. What if we have unlabeled data? What if the data is unlabeled? If the data is unlabeled, that is, so you take any industry application where we are not going to have ready-made supervised data that we can take handy and train deep learning models. So this is the realistic setting where the data is unlabeled. So if the data is unlabeled, now can we use can we annotate the entire unlabeled data and train our models, so that the model will be better, the model will be generalized across different domains. So this is where people started thinking of a domain or a research problem called active learning, because when you are going to have millions or trillions of unlabeled samples, now I cannot put the entire project project budget on annotation itself. So among those trillions of unlabeled data, I have to wisely choose which samples are important for the problem. Those samples we have to annotate instead of annotating all those trillions of samples. So this is the direction where people started working with active learning. Uh, yeah, just let me raise one more question here. Let's take data set like ImageNet data set, where we are going to have, I think we have 2 millions of images. Now, do you think all 2 million images are important for a training model like VGG16? Yeah, for that matter, even the current transformer-based models, do you think every image or every sample from this 2 million are important for model training? So this is the one more question that people started thinking. So they have come up with something called active learning. Now, let me just set the motivation for active learning. So basically, I would like to give some questions why people started thinking of something called active learning. So I would like to just touch upon this meme here, where let's assume we are going to have 1,000 samples, maybe 1,000 images. These 1,000 images are smartly selected or wisely selected using active learning. Now, having these 1,000 annotated images or 1,000 samples which are annotated for whatever supervised learning task, and on the other side we have 10,000 images which are labeled manually. Now, so the the one thing interesting that we are supposed to note down here is if you employ active learning, that takes care of what is needed in the training set. So how your training set has to be, then this is much better for the model compared to 1,000 images which are labeled manually. So we'll see what are how this active learning. So what is this active learning methods are? How we are going to make sure that what is needed for the model, how we are going to sample such data for annotation. So before going about talking about the active learning system, so let me discuss these questions that are based on which actually motivated the researchers and industry people to start thinking about active learning. So the first question is, why do we need efficient annotation methods? Because we have limited resources and high annotation cost. Because if I am not going to make this annotation efficient, then I'm going to end up with putting more than 50% of the project budget towards annotation. That is the reason why we have to be very efficient and effective while making the choice for annotation. Then how can efficient annotation methods address these challenges? So if you use this efficient annotation methods, so-called active learning based methods, maybe in fact the idea that I have discussed, that is semi-automated labeling. Even people also started about this semi-automated labeling, but this semi-automated labeling, it is not going to make sure that whatever is needed, what kind of samples you are expecting in the training set, that may not be achieved using this semi-automated labeling. But we'll discuss what is actually needed in the training set to train a machine learning model. So now the next question is, how can efficient annotation methods address these challenges? So these efficient annotation methods, they are going to reduce the annotation cost, and they are going to improve the data quality, that is training data quality. And so we can achieve the required project guidelines within the time because of the accelerating of annotation process. It is not just that, even so since we are going to uh, wisely choose this training sample, it is also going to reduce the training time of your model. For example, if you are going to train this model on the entire data, it's so where we have manually pooled all the data and labeled them. So if you are going to train your model with maybe let's say millions of images, the training time will be huge compared to just take some few thousands of images using active learning kind of methods. And if you train, that training time maybe come down to some days, maybe couple of days. Now the other thing is, what are the benefits of cost-effective annotation? So if you are going to make use of this, if you are going to make sure that the annotation is cost-effective, then so we are going to achieve the project deliverables on time, and also we are going to make sure that the required model performance can be achieved with limited amount of samples. I hope this at least these three questions give you the intuitive understanding of why active learning is important, why people have been adapting this active learning for many, almost many of the deep learning projects. Now let me spend some time on discussing this active learning system, where the active learning so yeah, as I told you, this active learning is going to have a huge pool of unlabeled data. So this is the unlabeled data set for us. Now what we are going to do is, from this unlabeled pool, we are going to select few samples. That few samples we may randomly sample from this, such that let's stick our understanding for object recognition or image classification. From this unlabeled pool, we are going to select maybe something like some 20,000 sample, uh, such that we are going to have equal number of samples from each category. That 20,000 samples we are going to uh, annotate them manually, so which we called as initial training set. Now using this initial training set, we are going to train a deep learning model. So this deep learning model will be this deep learning model we are going to make use as a candidate model. So this candidate model will be used to select the next set of samples that we wanted to give it for annotation. Now so now this unlabeled pool, we have selected some 20K initial samples, but it will be having even trillions of images, right? Apart from these 20K images, whatever remaining images are there, that remaining images you can feed it to this deep learning model, so-called candidate model. Now this candidate model will give, so if you feed this model, then it is going to give some feature map, basically a feature vector for every sample. Now using this feature vector, we can use some query strategy here. So this query strategy, we'll see what do you mean by query strategy here, and we can use some query strategy here. Using this query strategy, among this huge amount of images, we are going to select only limited samples based on some query strategy. Now these selected samples, we are going to feed it to the database, which in this case we call it as our annotator. So we are going to feed these images to the annotator. Then we'll get the labeled images for these selected samples. Just hold on. Just to make this concept clear. Initially, we are going to have 20K images that we have randomly pooled from this unlabeled pool. These 20K images are labeled manually with the annotator. Then this will be used as the initial training set to train this deep learning model. Then the deep learning model will be used to get predictions for the rest of the images or the remaining images. Now here we are going to have the feature map or feature vectors for every image. Using some query strategy, we are going to select, we are not interested in taking all the samples for annotation, but we are interested in taking we are interested in taking only selected samples for annotation. Let's assume here in this case we are going to select another 10K samples or maybe another 5K samples here. Now this 5, so this is again a hyperparameter here. So based on the resources you have for annotation, or based on the budget you have for annotation, based on that we can take a call on how many images you want to select. Let's assume in this case I have selected 5K images. Now this 5K images will be fed to the annotator. We'll get the 5K labeled images. This will give it to model. So now in total we'll be having 20K plus this 5K images. Now totally we'll be having 25K images. Using this 25K images, we'll update this model. We'll update this model so that we are making this model to get updated using the samples that we have wisely choose using this query strategy. Now, essentially what we are doing in this cycle, in this pipeline of active learning, in this pipeline of active learning, we are trying to update, we are keeping the model in loop, and we are updating this model such a way that this model, it is going to select the samples, better and better samples in the next iteration. So again, we are going to update this model now. So basically, let's assume the total number of samples it has initially is n. Then the initial samples that we have pulled is 20, and the next we have selected 5 more samples. 5K samples here. Now the unlabeled pool, it will have n minus 25K. Now this n minus 25K samples will be again given to this deep learning model. Now for this n minus 25K samples, it will give the feature vector if you feed it to the model. Then again we use query strategy. Then we are going to select again 5K samples. These 5K samples are fed to the annotator for labeling. This 5K images, we are going to add it to the training set. Now it will become 30K samples. Yeah, using this 30K samples, we can train this model. Maybe here the one more question that you may think of is here, the moment we start with this 5K, the moment we start with this 5K, the model has already seen this 25K samples. So do we need to still use this 25K samples while training with this 5K samples, or since the model has seen this 25K samples already, can we just train the model with 5K samples alone? Yeah, still that is possible. Yeah, even people also started in that direction, where instead of training the model from using the entire data set again and again, you can just use the samples that you have extracted or selected in that iteration. You can use those samples to train the model. So again, we update this model. So now this model will be gets updated continuously. So this model will be used to again, now it will actually n minus 30K samples. Again, this images will be fed to the model so that we'll get the feature vector. This process repeats. This system, it repeats continuously until maybe something like you have some budget for the annotation. You have some annotation budget. Until this annotation budget is repeated, until this annotation budget is achieved, you can repeat this process. Maybe let's assume your annotation budget is something like some 2 lakh samples. So until that, you can repeat this process. You can make sure that we have selected the samples in a wiser way. And I'll discuss these methods. What is this query method? How can you dynamically change these query methods based on your understanding of model performance? So I think so this is the end-to-end active learning method. I hope you understood this end-to-end active learning method pipeline. Now let me move on to so in the previous slide, when we were talking about this end-to-end pipeline, where so we were talking about query strategy, right? Now let me elaborate more on what do you mean by this query strategy. Now the objective of this query strategy is we have huge amount of samples here. Maybe in this case it is a feature vector, but it is a sample. It is corresponding to each sample. Here we have huge samples. Of this, we have to select a few samples. To select few samples, we are going to use some method here. So that method is called query strategy. So these methods that are used to select samples for in each iteration are called sampling methods or active learning sample methods. Now let me just talk about what are the different active learning sampling methods that we have in the literature. So let's take it's like a population or a distribution which is having n number of samples. Of this, I'm interested in selecting one sample per category. That sample represents that sample represents maybe a group of people. So if you select samples in this way, whatever model you are going to get uh, by training using all the samples, and versus the model that you have trained with only these 5 samples, will be having roughly the comparable performance. For example, so let's assume you have maybe around some 3 lakh samples. Now, which are all of these samples you have used, and you have annotated them manually, and you are going to train this model. Let's assume so using this trained model, so the model is going to give something like 85% precision or recall, whatever, maybe 85% accuracy on the test set. Now you are going to use this active learning sampling method, and you select around some 1 lakh images. Now, so even if you are going to get some accuracy, something like 84%, still we are fine with this because the performance is comparable here. The performance is 85% and 84%, it is comparable, but I have reduced the annotation cost significantly. So if this is the requirement, so that's where we can use active learning setting. Now let me just talk about this different active learning methods that we have in the literature. So one direction is uncertainty sampling, where if the model is uncertain about sample, so whichever samples at which model is very uncertain, so those samples can be chosen for further model training. For example, let's assume there are let us consider this is in total some 30 images or 30 sample. Let's assume the model is very accurate, it is very confident on this sample. It is very confident on this sample. Means whatever the initial candidate model that we have, so this candidate model is obtained using the initial training set using which we have trained the model. So this is the candidate model. If the candidate model is very certain or very confident on the category of this image, let's assume this is one object, this is one image, this is one image. So if this is saying this belongs to human category with 99% confidence, it means the model is very confident on this subject. So similarly here, this is one more image. Let us consider this is one more image. So again, this image, if model is saying with 98% confidence, this belongs to human category, still the model is very certain about this image. But there are some images in the unlabeled pool. Let us consider this is the unlabeled pool. In the unlabeled pool, there are certain images at which model is very uncertain. For example, let's take this image. This image, let's assume the model is very uncertain. Maybe it is saying this belongs to human category, but maybe let us assume it is saying with something like 0.48 confidence score. That is with the 48% 48% confidence score. So now in this case, compared to these two images, the model is very uncertain about this sample. Now, the idea is pool or choose the samples at which the model is very uncertain. Means the model select the samples at which the model is least confident on. So this is one sampling method. So what we could do is, if you go back to the previous slide here, so instead of getting the feature vector here, you feed the unlabeled pool, the remaining data from the unlabeled pool, you get the confidence score for each sample. Now just see what are the samples at which model is least confident on. Of those samples, maybe you can select the top 5k samples, at which model is very least confident on. So those samples can be selected and they can be given for annotation. So that is what this least confident method talks about. So under this uncertainty sampling, there is one more sample called marginal sampling. What this marginal sampling says is, let's assume we have a 3-class problem where let us consider this is unlabeled sample. There are two unlabeled samples, unlabeled sample 1 and unlabeled sample 2. If you feed this unlabeled sample to the model, then model is going to give the probability score for each category, right? Let's assume it is going to give 0.4, 0.4, and 0.2. And for the second sample, it is going to give 0.9, 0.05, and 0.05. See, if you just apply the least confident method, if you just apply least confident method, what we are going to do is we are going to select instead of selecting this S1, we are going to select S2, because at this sample, sorry, we are instead of selecting this sample, we are going to select this sample because the maximum confidence score is 0.4. It means the model is least confident compared to this sample. We are going to select this sample. But if you go to this marginal sampling, what marginal sampling says is, let's take the top two predictions, means the top two confidence scores predicted by the model. In this case, this is this one and this one. So whereas in this case, this is 0.9 and 0.05. It could be this 0.05 or this 0.05. It could arbitrarily, we can take any one. What margin sampling says is, select the sample or choose the sample for which the difference between the top first confidence threshold and the first confidence score and the second confidence score is minimum. Select such samples. For example, in this case, maybe let me do one thing. I'll make it as 0.5. So this is 0.4. Let's make it as 0.1. Yeah. So if you look here, so here the difference between the first confidence probability score and the second highest probability score is 0.1. Whereas here, so the first, it is actually 0.85. Now, what this marginal sampling says is, select the sample for which you are going to have the least difference between the highest probability score and the second highest probability score. It means what? The model is unable to distinguish whether the sample belongs to this category, first category or second category, compared to this image. So in this image, it is clearly saying that with 90% probability, it is saying it is belongs to category 1 or class 1. Whereas here, there is a dilemma. So instead of just selecting the least confident samples, you select the samples for which this margin or the difference between the highest probability score and the second highest probability score is minimal. So that is what this marginal sampling method says. And now coming to diversity sampling. So it is not just about taking the samples which are uncertain, but we have to also make sure that the training set is diverse enough. Diverse enough in the sense, for example, we are working with object detection problem. Now maybe object detection, so it is very generic. Let's take face detection problem. Now let's assume we are working with face detection problem. When we say diversity sample, now we want training set where the training set going to have images from daytime and also nighttime. And we need to have the images in the indoor scene and also in the outdoor scene. Basically, it means it should cover all the variations. So if you are if you are going to have the training set where you are having 90% of the samples in from daytime, just 10% of the samples from nighttime, it is as your training set is more biased toward daytime. So then what will happen? Essentially, whatever the face detector you are going to build, that will work really well for daytime, but it may not work well for nighttime. So that's the reason why we have to select the samples based on diversity. Very diverse samples you have to select. I don't want to get into these methods in detail. So there are other sampling methods like density-based sampling and the expected model change. So maybe here again there are very many variants like change in the gradient. So the some methods based on the so which are used for transfer learning. So these are the different sampling methods that are used in literature for active learning. Now, particularly talking about, I would like to give this example just to say we were talking about some uh, well-respected sampling methods in the literature. Now, at least let me give a setting where I worked on a problem where we have to choose the sampling method based on our requirement. Let us take, so this is the image that I took while I was working for Litex. So I have been involved in a project where so I need to build a deep learning model to predict road condition and also the weather condition. Here the immediate requirement for our clients was we have to come up with a model, AI model, where that model should do very well for heavy rain or heavy snow. So first build a model. So clients are very interested, very keen on first getting a initial version of the model that do very well on heavy rain, because their requirement is detecting heavy rain first or predicting heavy rain first compared to light rain. Even if your model is not going to perform, the initial model is not going to perform well for predicting, even if light rain cases, still we are okay, but we are very interested in predicting heavy rain and heavy snow. So if this is the requirement, just think about the model. If you train a model that is for maybe let's assume road condition detection. Now, so whatever the candidate model that you are going to have, so which is trained on the initial training set, it is so you can intuitively feel that the images at which we have the heavy rain or heavy snow, these are very easy samples. Means at these samples, model is very confident. Maybe it may say that, let's assume this is rainy case, this is snow case. Now the model can say that with maybe 95% confidence, it will say that this is belongs to rainy category. So with 98% confidence, it may say that this is belongs to snow category, compared to the images where there is a light snow. So if you have light snow, if you have some images in the unlabeled pool, if you have a light snow images, maybe for those images, the model may say that it is belongs to snow category, maybe with 50% confidence, that is with 0.5 probability score. But in the unlabeled pool, if there are heavy snow images for which model may say that with 0.9 probability or 0.9 confidence score, it belongs to snow category. So since my requirement is heavy rain, my requirement at the initial model I have to build is heavy rain. So instead of choosing the samples that are with least confidence, we can choose the images with the high confidence. Though the model is very certain about these samples, then still my requirement is to make the model good at heavy rain images or heavy rain samples. So I am still interested in going with choosing the samples based on high confidence. That is, so we can choose images with high confidence score. So then we can build a model until we get a stable model that is doing well for this high confidence sample. Then you can start adding the low confidence samples to this. Then what will happen the moment you add high confidence samples and low confidence samples? So the model will try to generalize it for both heavy rain and low rain cases. Similarly, heavy snow and low snow cases. So with this slide, what I would like to emphasize is this sampling method, whatever we have discussed in the previous slide, that may not be relevant for the problem that you are going to work with. So this you may have to think more on the requirement. Based on the requirement, you have to come up with the sampling method. Yeah, so just I have kept this slide just to summarize the learnings that I had myself and my team had with while working with this active learning. So since this, yeah, this is actually raising one interesting research question. Select the initial samples. So though in our case we have selected randomly, select the samples and label them. Then you get a candidate model. These candidate models can be used to pool the next set of samples. So one more learning that we have is so these AL sampling methods may work to some extent, after which you have to analyze the data, means you have to analyze the results. Based on your analysis, you may have to change the sampling method. And one very evident is this active learning is definitely going to accelerate industry ML projects. These are the three learnings that we had. Now just let me conclude on the today's talk. We have seen this few shot learning, where this is where we are going to use this few shot learning when we have few label samples for specific categories. That is, when your data is completely annotated, but there are some categories for which you have only few labeled samples. So that's where we are going to use few shot learning. But these days even people how to fine tune the model without coming across that catastrophic forgetting problem. So due to time constraint, I could not talk about this fine tuning part, where I mostly talked about the idea of learning the similarity function. So so at the end I have given some references. Please feel free to go through those references. You'll get the understanding of this few shot learning methods based on the fine tuning. And active learning, as we have seen that it is a promising approach to make the annotation efficient and effective, so that you can complete the ML projects in the given deadline. These are the few of the references that I have went through while preparing the slides for this talk. Yeah, so I am done, Professor. If there are any questions, I would like to take the questions.
Yeah, so thank you, Sabir. As usual, your talk was very wonderful. So now I request the participant if they have any questions, so they may feel free to ask. So Sabir, you may also check the chat box. So some comments are there.
Yes, yes, yeah. See, for example, let's assume the yeah. In fact, this is a very interesting question. At least I could start thinking this question, and recently we started applying this. Let's assume the one real-time example that I would like to give. Let us consider where I would like to build a people detector for night time. So if you are going to pull the initial sample, because I don't know the initial samples, whatever I am going to pull, which I am going to pull randomly, those samples I may pull from both daytime and nighttime. So intuitively we can feel that the object detection model that you are going to uh, train, that model may do well for the daytime cases. But let's assume, what if the requirement from the client is the initial requirement from the client is building people detector for the night time, at which basically you have to choose the images at which model is least confident. Hope this example is clear for you.
So is there any other questions? Okay, I think Sabir, no more questions. So thank you very much for joining this session. So now I think we can close this session.